down then on how much we have to write and give us more time for other things. So what we are going over to start off with now today for one of our goals is more or less vocabulary. Common vocabulary that we use to describe different elements on the periodic table. So if I go to my first slide here, come on. You should see on your note sheet, across the very top, it has numbers 1 through 18, and above it is the word group. Group is simply referring to those different vertical columns. So if I talk about group 2 elements, you know I'm talking about beryllium down through radium. A period is a row across. And what do you know? Those periods are numbered kind of the same way that you numbered your own periodic table for the different shells or energy levels. Now again, I tried to emphasize that electron configuration plays a role in the shape of the periodic table. But actually there's even more with the shape than just that. What we're going to find over the next week or so when we start talking about what are called the trends of the periodic table is elements in a group often behave in a similar manner. Now if you behave in a similar manner versus other people, sometimes you consider that to be family. For example, I have a brother. He is redhead. He is tall and skinny. He runs. Check, check, and check. That we behave in a similar way. So it's similar with the periodic table as well. So again, first slide, be aware of those vocabulary terms. Now, the word group is on your own periodic table above the first column. So if ever you had to know between a group and a period, group is listed on yours. The word period typically isn't stated on your periodic table. Next, the periodic table contains elements that are metals and nonmetals. Now this might be nice for you to get out your periodic table with right now. Because the first thing I mention on here is notice the staircase. There is a staircase on your periodic table, and the one on your note sheet is kind of color-coded a little bit as well. Some students like to really outline that. So maybe you want to right now make sure you put your mark on that. Make it really stand out. Because with everything to the left of that staircase are metals. The exception being hydrogen. Everything to the right of that staircase is nonmetals. So even that some students write on their periodic table with. Metals are to the left, excluding hydrogen, because hydrogen's a nonmetal. Nonmetals are to the right. The vast majority of the elements are metals. Now some of them we recognize as metals. Aluminum is right next to that staircase. We recognize that as a metal. Gold, silver, sure. But some of them, like sodium, we don't think of sodium as a metal, because when we think of sodium, the first thing you probably think about is sodium chloride. Although that's a little bit different than a neutral sodium atom. And we'll go over that. Again, hydrogen, even though it's a nonmetal, is put on that left side, dealing with the fact it has one outer shell electron, just like everything else does in that row. And we're going to go over that a little bit in our notes here as well. Now, on your note sheet, I have this exact same picture. Kind of a comparison between metals and nonmetals. We will go over something called metallic bonding in the next unit. And when we go over metallic bonding, we're going to go more into those properties of things. Like metals are very good conductors. After all, if you cut the cord on something that you plugged into the wall, you probably see some copper inside of there. Copper is an excellent conductor. I think there's one metal that's better. Gunter, do you? Is it silver?
I think silver.
Now, we don't make silver wiring for everything because it costs too much. Quite frankly, copper costs an awful lot too. Some people, when their homes are being built, people will go in and steal the copper out of it because copper is very expensive. Remember, the penny isn't much copper in it anymore either because it's too expensive. So I'm not going to focus too much on the properties right now between these two. because that is something that we're going to dive more into next unit. However, you recognizing which elements are metals and which elements are non-metals, that's something that we need to be able to do today. Okay? Now, really, where is your dad from? Okay, Illinois. Is he near the Illinois border or southern Illinois? So right from Chicago. I ask Wrigley because I know her dad is a Cubs fan, right? Some people from Wisconsin are actually Cubs fans. I know, Connor, that just feels wrong. But when you are close to the border between Wisconsin and Illinois, I mean, if you live in Kenosha, you're awfully close to Chicago. So I wouldn't blame you if you were a Cubs fan. Just like if you lived out in Eau Claire and you're close to Wisconsin-Minnesota border, you're actually closer to the Twin Cities than you are to Green Bay. So if there's some people from Eau Claire that are Vikings fans by chance, and nobody's perfect, I get it. But I understand why, because of that proximity. That staircase is the border, if you will, between metals and non-metals. However, if you are right on the border, like some of these elements are, silicon, germanium, arsenic, antimony, for example, it's not just I'm a metal or I'm a non-metal. It's a little blending of the two. And that is what metalloids are called. So on the very bottom of your note-taking sheet, you see there's a blank there, which, by the way, if you didn't fill in 2 blanks earlier of metals and non-metals, you should do that as well. But those elements that are on that staircase, those are referred to as metalloids. Have some properties that are like a metal, but not completely. And I also use the example, if you're on the U.S.-Mexico border, there's a chance that you speak English and a little bit of Spanish as well. Because in your daily life, you might encounter people that do both. It makes sense. I mean, heck, in Canada, Quebec has French speaking very common, but again, the further away you get from Quebec, the less likely you have to know any French. But if you're right next to Quebec, there's odds that you have to speak English and French there. When you're on that border of that staircase, that means you're a little bit of both. We call that group the metalloids. And that's kind of what we're going to be doing with our back page of this right now. So if you flip to the back page, we call that group metalloids, or that cluster of elements metalloids, because they behave in a similar manner. They're a little bit metal, a little bit non-metal. We're now going to focus on individual columns of the periodic table, because some of those columns have certain behaviors. So, for example, group number 1 is your alkali metals. Skip through all of these points here. Okay. Now, group 1, excluding hydrogen, so lithium on down to francium, is what we would call alkali metals. After you write down alkali metals, notice that there's a space on your notes where I want you to write the shorthand notation for potassium right now. I want you to do that because the shorthand notation, ladies and gentlemen, shows how many outer shell electrons you have. Remember, our fancy term for outer shell electrons is valence electrons. Now, some of you are simply looking up the answer in your periodic table. That's perfectly fine. Some of you are actually trying to figure out, go to the previous noble gas. That's good too. It doesn't matter if you're lithium all the way down to francium. Those alkali metals have similar properties, of which I have listed up on the board, which you already have on your note sheet. Since they are metals, they are good conductors of things like electricity. However, they're softer than what you consider most metals. If we have time today, the very last thing I have mentioned here is to do a demonstration with sodium metal. I have a big chunk of it, and I can cut it with a really dull knife. But you wouldn't think a chunk of gold you can cut with a knife. Well, these are softer. And what I think is the most interesting about alkali metals is this last point I have up on the board. The majority of our planet's surface has water. The majority of what makes up your body, water. Water is pretty tame. Because if it was really reactive, it would not be water anymore. It'd be something else. It would change into something else. Sodium metal, along with our other alkali metals, are so reactive. If you put that in water, it's going to violently react. Again, if we have time to today, we're going to show that to you. Otherwise, it might be something we save for next time. But heck, it's so reactive, I have to store it a special way. I have it inside of a can right here, and inside that can is a second bottle, and it's covered in oil. Heck, I have to have a special fire extinguisher. When you think of fire extinguishers, you think of guys like this. This would do me no good if there's a fire with sodium metal. It's kind of weird, but I have to use what's called a Class D fire extinguisher in order if I had a fire with that. So, lithium on down to francium are the alkali metals. What we're going over today is common vocabulary that you do need to be aware of, that you are responsible for when it comes time for your quiz next time. Second column is the alkaline earth metals. Now, I'm not going to put down quite as much for them. This is the second column. And they are reactive, but not as reactive as the alkali metals. So this is beryllium on down to radium. Things that are reactive are typically not found on their own. They're found bonded to something else. Like sodium, you just don't find sodium laying around in nature. It's going to bond to something else. That reason for bonding we're going to start to get into later in the class today. So we'll talk about sodium chloride specifically. Again, on your note sheet, if you haven't already, make sure you write down the shorthand notation for strontium, it looks like. Strontium is element 38. However, if I told you it was an alkaline earth metal, you should know to look in the second column and you'll be able to find it fairly quick because there's only so many of those. Notice how it ended in a 5s2 because it's 2 valence electrons. We okay? Now, we have just covered the first 2 columns of the periodic table, recalling that hydrogen is not a metal. Should we do this for every single column on the entire periodic table, folks? Well, what if I name it after you guys, though? Here's the Sam column. Here's the more. No? Okay. Let's speed things up. Everything in the middle. Let's just give it a name. So everything in the middle is going to be called transition metals. So kind of that d orbital is what we're going to be talking about here. Now again, you can look at your note sheet and do a couple things. One, you can look at the same things I have up on the board here. But secondly, I'm asking you right now to write down the shorthand notation for zirconium, so Zr, that's element 40, and element 42, Mo. Because if you write down the shorthand notation for those two, you will notice that they do not have the same outer shell configuration. I can't say something nice and neat like it always has 2 outer electrons. And look at your shorthand notation. Mo is one of those tricky ones, those half-filled orbital ones. Transition metals, they can be reactive, sure. However, they can also be found alone, like gold. Gold can be found on its own. I mean, my wedding ring is gold and platinum. If it was a reactive metal, it would not be existing as it currently is. And that means my ring would break down over time, and you don't want your ring to rust necessarily because that's reacting as well. It just wouldn't be the same. So some of these metals are very unreactive, some are a little bit reactive as well. And then the very bottom 2 points here talking about general properties of metals. They're good at conducting heat and electricity. They can be made into wires or hammered into shapes, ductile and malleable. So when you think about how did we make this like this, well, someone shaped it that way. You can do that with metals. You can't necessarily do that with non-metals. Okay? So, we sped things along, and we just covered all this middle. By the way, on our note sheet, hopefully for ZR, we call that KR 5s2 4d2. And for MO, we call that KR 5s1 4d5. And for half filled. Okay? Okay. Not only was it good news that we're not going to name every column, some of them we're just not going to name at all. For example, we're not going to give a name to boron on down. Boron is above the staircase, it's a non-metal. Things below are metal. Well, if you're a metal versus a non-metal, you're not going to behave the same. And if you don't have similar characteristics and similar properties, you're no longer a family of the periodic table. Same thing for carbon on down. We're going to ignore that column. We're going to ignore nitrogen down. We're going to ignore oxygen on down. And that barely has one thing that's in that staircase. And that thing's radioactive. So we only have 2 columns to go. The second to last column on the periodic table is the halogens. Now, as I mentioned, they have 7 valence or outer shell electrons. I'm asking you to write bromine shorthand notation as an example of that on your note sheet. And you can look directly on your periodic table if you'd like to. These halogens are non-metals. They're on the right-hand side of the staircase. And they are very reactive non-metals. They're like the counterpart to the alkali metals that are reactive metals. As a matter of fact, they often react with them. And I did mention on the bottom here, remember the color coding on your periodic table. Elements that are in black are solid at room conditions. Blue is liquid, red is gas. So that's the only family that they still behave similar in how they react. However, they do have all 3 states of matter. And that gets into something different called intermolecular forces that we will cover at the end of first semester. Now, when you wrote down your shorthand notation, hopefully for bromine, you wrote down AR in your brackets, 4s2, and a 3d10, and a 4p5. Okay, maybe that's not in the same order. Maybe you did 3d10 first because you wrote it straight from the periodic table. But 4s2 and 4p5, doesn't matter if it's S or P, in the 4th shell, the outermost shell, there were 7 outer shell electrons. Okay? The last family of the periodic table are the noble gases. And this is the last column. Now, I'm not asking you to write down shorthand notation on your notes. I'm asking you to write the normal notation for neon and for helium. Because when you write down neon, you should notice that there's 8 outer shell electrons, 2s2, 2p6. Those 8 outer shell electrons is what we mentioned last class when referring to what's called the octet rule. Elements are more stable if they have a full outer shell. We'll talk about that again later in this hour still. But because of that, they are very unreactive. You can breathe in helium balloon, and that's not going to react with anything that's going on in your body. You just have to make sure to breathe in other gases too so your body can survive. Now that octet rule applies for most things. However, I did mention helium is also unreactive. Helium, you should have wrote down 1s2. But that 1s2 means it's a full outer shell. Some of you on that sheet last class didn't get to the very last problem. It references helium, things like a lithium ion, for example. So in general, even though it's not perfectly correct, when you have an electron configuration like these last noble gases, we refer to that as the octet rule. And just like I had subject-specific clothing when I first talked to you about gaining and losing electrons, Again, I bring out more clothing for you guys today of my Noble Gas shirt. Mr. West gave me compliments about this one today as well. I probably won't wear this again for Monday's class, but I do have a shirt that's based upon metals, so I'll probably wear that one instead. It's important to have subject-specific clothing, Eric, when you're teaching this stuff. Very important. The very last blank on your note sheet should be for main group elements. What we are going to start to dive into next week after our quiz, I already mentioned it once, is what we refer to as the trends of the periodic table. These trends are going to help us show which elements are more reactive and why. Typically, because the transition metals vary in their number of outer electrons, half-filled, not, and some of them are very unreactive as well. Typically, when we talk about the reactivity elements, next week we're going to focus more on the first two columns, the s orbitals, and the last six, the p orbitals. The name we give to that is the main group elements. So, okay, so an ionic bond is typically formed between a metal and a nonmetal. Now, there are going to be a couple exceptions that we'll get into in the next unit, but remember, metals are on the left side of the staircase, excluding hydrogen. Nonmetals are on the right. So, grabbing a little bit of each. Two more vocabulary words that you need to be aware of, which on your note sheet is asking you about, is cation. This isn't cation. This is cation. And anion. And here are the definitions of both of those, which we've already been working with cations and anions, and we've been writing electron configurations for things with charges. Now, again, today's like a biology class with all the vocabulary we're going over, it seems. But, Kirby, I'm going to help you know these terms. We start off with mold jokes, which I didn't get much of a response for, ladies and gentlemen. I'm a little disappointed. Okay, wardrobe-specific clothing for what we're doing today. To help remember the difference between these two. You ready, Katie? Cations are positive. I'll take the type noise that we just made there. That's not a full-blown laugh, but it's something. That's how you remember this. Cations are positive. Now, you'll learn if you take enough chemistry, the prefix cat and the prefix an deals with positive versus negatives for more than just ions, but two terms that are very commonly used. So looking at your note sheet, we should have already covered 1, 2, and 3. How do these things get a charge? Remember, protons don't change. When you give something a positive charge, that does not mean it gained positive protons. No. Electrons can be gained or lost. And if you lose electrons, you become positive. You gain electrons, you become negative. When you answer that number 4, why don't you look at that picture in the middle of your note sheet? And number 5 says, what elements are shown? So I'm giving you a Bohr diagram for neutral atoms. I think that would help out to say that they're neutral atoms. Identify the two elements based upon their electrons shown in that number 5. Again, that same picture is up on my board right now, but it is not sodium and chlorine. So again, look at that picture on your note sheet, which is the same as I have on the bottom of my slide here. What element is that on the left-hand side with 3 total electrons? Lithium. And you have 1s2 and you have 2s1. What element is that on the right-hand side? Chlorine. 1s2, 2s2, 2p5. And you should hopefully notice on that picture what's happening. The lithium is losing an electron to the fluorine. When lithium loses an electron, it will now have a charge. What would the charge of lithium be if it lost an electron? Plus, or plus 1. Fluorine is gaining a charge. Because it's gaining an electron, it would be a minus 1 charge. And once again, just like when I showed you the cathode ray tube experiment, if you remember what you were taught way back in elementary school about opposites attracting, that's what an ionic bond is, ladies and gentlemen. Sodium chloride is Na plus and Cl minus. They stick together because they're oppositely charged particles. So when you look at your note sheet, how are atoms held together? That's what my first bullet point in the top here is trying to address. Give an example. Well, I gave you 2 examples here. The NaCl, for example, is table salt, although there's a little bit extra in table salt. But it's primarily NaCl. The calcium with 2 chlorines is the second example. It doesn't have to just be plus 1s and plus or minus 1s. It can be plus 2s and minus 1s. It can be plus 2s and minus 2s, plus 3s. Opposite charges attract. That's what an ionic bond is. In our next unit, when we do more bonding, you will learn that an ionic bond isn't really a true bond. It's more of just opposite things attracting each other, holding together. By the way, this Ca with 2 Cls, we used that in the lab already this year. Remember those little white dots that we put in the rainbow and let sit out overnight? Came back and they were all wet. That was the calcium chloride, the Ca with Cl2. So, an ionic bond is an attraction between 2 opposite things. If you flip to the back page, this again deals with a very important rule within chemistry, which is called the octet rule. Last class, you did a sheet where you had to write down electron configurations for a lot of things. And it was said that these were the most stable form. And hopefully you picked up on a pattern. And that pattern was that a lot of things ended with 8 valence electrons. That gave it a full outer shell. There was no more room for anything. The octet rule is our main rule of bonding in a chemistry class. Whether or not you're an atom or an ion, stability is based upon that full outer shell. Once you jot this down for that answer, what I would like you to do on your note sheet for number 8, A and B, is draw the orbital notation for both sodium and chlorine. Remember, orbital notation is the up and down arrows. So take a couple minutes right now if you need your periodic table fine. But again, I want the up and down arrows. Orbital notation for a sodium atom and a chlorine atom. And what we're going to do, ladies and gentlemen, is we are going to show you this, and then we're going to stop here. So there is a little bit more to your note sheet that we're not going to get to today, but I'm okay with that, because I want to make sure to end the class with doing more practice with electron configuration with transition metals. So I'm going to give you about 30 more seconds, and then up on the smartboard, I'm going to draw both of these out. And that might address some of those questions towards the bottom. But I want to make sure we have time to go over things. Hopefully that's what you have written down for sodium and chlorine. 8 outer shell electrons is the most stable configuration. How many outer shell electrons does sodium have? 1, right? But if it lost that 1, and that 3s is gone, now how many outer shell electrons would it have? 8. That's why in sodium chloride and other sodium compounds, sodium is a +1 charge. Sodium's not going to be a +2 charge. If it lost one of these, it's no longer stable. Chlorine. How many outer shell electrons does chlorine have? 7, right? Between the S and the P, then that third shell, it has 7. So it is going to gain an electron. As a matter of fact, sodium and chlorine kind of work together. Well, they can both be satisfied at that octet. Metals lose electrons. Non-metals gain electrons. Now that idea then leads us into the fact that they have a charge. And that causes them to stick together as well. You help me, I help you, now let's stick together throughout this. But we're going to stop at that point, because even though ionic bonding itself is not in your quiz, again, we're using stuff that is going to be on your quiz, and I think that's important for us to kind of stop at this point before we go any further.